So in this video, we're going to continue talking about dissociation of water, and we're going to introduce the pH scale, right? The pH scale as a way of reporting the concentration of hydrogen ions in solution. Okay? So if we look at the normally useful ranges for the concentrations of hydrogen ions and hydroxide ions in solution, remembering that they're connected by an equilibrium, the common concentrations are from about 1 molar hydrogen ions down to 1 times 10 to the minus 14 molar hydrogen ions, or 1 molar hydroxide ions down to 1 times 10 to the minus 14th molar hydroxide ions, right? And right in the middle is this 1 times 10 to the minus 7, where both hydrogen ion and hydroxide ion concentrations are the same, right? They're equal to each other at those concentrations, right? The KW tells us that at 25 degrees. But this is, right, 10 to the 14th change, right? 10 to the 14th, let's see, 10 to the third, that's 10 to the third is 1,000, 10 to the 6th is 1,000,000, 10 to the 9th is 1,000,000,000, 10 to the 12th is 1,000,000,000,000. That is 100 trillion, right? There's 100 trillion times difference between this concentration and this concentration, or between this concentration and this concentration, right? We're not used to dealing with numbers that range over 100 trillion, right? And the other thing is, part of the reason we limit ourselves here, right, is if you get more base than this, the base starts to react with water in different ways. And if you get more acid than this, our strong acids stop acting like strong acids and start trying to reach equilibria. So we sort of limit ourselves to this range most of the time in aqueous solution. But we got to deal with this range of 100 trillion, right? How do we do that? Well, the way people did that or dealt with that is to convert these large exponential numbers into log numbers. But since the exponents all the way across here are negative, right? You don't like to deal with negative numbers all the time, right? So they defined the pH, right? P, whenever you see that P, it is the negative of the log of whatever the quantity is. So it is the negative log of, in this case, the quantity is the hydrogen ion concentration, right? So if the concentration of hydrogen ions is 1, the pH is equal to the negative of the log of 1. The log of 1 is 0, negative 0 is 0, right? And if we move to, right, if the concentration of hydrogen ions is 1 times 10 to the minus 14th, the pH is equal to the negative of the log of 1 times 10 to the minus 14, which is, right, negative 14, negative, positive 14. So now we convert this range of 100 trillion into a range of 0 to 14, and that makes it easier to deal with, okay? And so we can always look at the pH of a solution. It's easier to report the concentration of hydrogen ions in pH than it is in just straight concentration, right? It's a smaller number to report. We don't have to worry about superscripts and subscripts. It's just easier to write down. Okay, so here's a straightforward problem. what is the pH of a 5 times 10 to the minus 3 molar solution of chloric acid, right? Chloric acid is one of our strong acids, so we know that chloric acid will dissociate completely into hydrogen ions and chloride ions, right? And if our initial concentration of this is 5 times 10 to the minus 3, we have 0 of that and 0 of that initially. Our change is going to be that all of that dissociates. Right? All of that dissociates. And so when we reach our final condition, we'll have no chloric acid left. We'll have 5 times 10 to the minus 3 molar hydrogen ions and 5 times 10 to the minus 3 molar chloride ions. We know then, from what we just defined, that our pH is equal to the negative of the log of the concentration of hydrogen ions, which is going to be the negative of the log of 5.0 times 10 to the minus 3, right? If I go back to my original significant figures, right? Not my lazy writing too fast significant figures, right? And so that is going to be equal to 2.30. Now, one note here, right? I noted the two significant figures. In log numbers, the only numbers that are significant are the ones after the decimal point, right? So this number is actually representing the two significant figures that we had in our original given number, right? So in this case, the pH is equal to 2.30, right? And so we can do that anytime we know the hydrogen ion concentration. So now we'll look at a base problem, right? What is the pH of a 2.0 times 10 to the minus 5 molar solution of potassium hydroxide? Well, right, we're still dealing with this is a strong base, so our potassium hydroxide will dissociate completely to make potassium ions and hydroxide ions, right? We should be getting the pattern, right, that if our initial concentration is 2 times 10 to the minus 5, that all of that will dissociate. And so when we reach our final condition, again, not in equilibrium because this is dissociating completely, we have none of our potassium hydroxide left. We have 2 times 10 to the minus 5 molar potassium ions and 2 times 10 to the minus 5 molar hydroxide ions, right? But, right, pH deals with hydrogen ions, and we've got hydroxide ions. And so we have to then go through our Kw, right, and our equilibrium, right? So our Kw is equal to the concentration of hydrogen ions times the concentration of hydroxide ions. And so 1 times 10 to the minus 14, if we're working at 25 degrees Celsius, is equal to the concentration of hydrogen ions times our 2 times 10 to the minus 5. So our concentration of hydrogen ions is 1 times 10 to the minus 14 divided by 2 times 10 to the minus 5 is equal to 0.5 times 10 to the minus 9, or 5 times 10 to the minus 10, and that would be 5.0 times 10 to the minus 10, right? And that would be equal to our hydrogen ion concentration, right? So our pH then would be the negative of the log of 5 times 10 to the minus 10 molar, right, which would equal 9.30. Again, right? The significant figures in a log number are the numbers after the decimal place, so that number is two significant figures, and our original information was given in two significant figures. Okay? So we can find the pH of solutions where we know the hydrogen ion concentration first. That's straightforward. If we know the hydroxide ion concentration first, we have to use the Kw to find the hydrogen ion concentration, and then we can find the pH.